I welcome you all for this lecture series on deep learning. In this lecture, why we should learn gradient computation in recurrent neural networks. The gradient computation is essential in a recurrent neural networks because it enables the network to learn from its mistakes while handling sequential data. Since RNNs reuse the same weights across multiple time steps, the network must understand how errors at each step influence these shared weights. Gradient computations performed using backpropagation through time (BPDT) helps determine how much each weight contribute to the overall prediction error across the entire sequence. By computing gradients, the RNN can update its weights in the correct direction to reduce errors, improve memory of the past information, and make more accurate predictions over time. Without gradient computation, an RNN would not be able to adjust its parameter and therefore you could not learn meaningful patterns from the sequential data such as text, speech, or time series signals. Let us see one by one. First, gradient computation in RNN. The gradient computation is the learning mechanism, that is learning process in a recurrent neural network. That means this computation is the in this mechanism of a recurrent neural network that allows it to improve prediction over time, and it evaluates how errors occur during the training and determine how much each network weights contribute to the total error. Since RNN handles sequential data, this learning process is carried out using the BPTT, that is back propagation through time, where errors are propagated backward across all time steps to update shared weights effectively. Next, let us take one example for this mechanism. Imagine a student Imagine a student. He writes a weekly test that has questions from Monday to Friday lessons. After getting the result, the student goes back from the last day to the first day, checks where mistakes happen, understand why they happen, and learn how to avoid them the next time. Gradient computation is the best example for this. In this computation, it works the same way. An RNN looks at all its mistakes in a sequence and learn from them going backward. Next, hidden state computation in the forward pass. The equation is given by hidden state. Ht is equal to here activation function wxh xt plus whh h of t minus 1 plus bh. So here the hidden state represents the internal memory of RNN at a time step t. It stores information from previous inputs and combines it with the current input to produce the new hidden state. This dependency on both past memory and present input allow the RNN to capture sequential pattern and the context during the forward pass. I'll tell you one example. Thinking of watching a TV series. For this example, I'm telling TV series episode we are looking into. When you watch today's episode, you still remember what had happened in the yesterday's episode. That memory helps us understand today's story better. The hidden state works like that memory, it carries past information forward. And how we are going to calculate the output? It has been given by the equation yt is equal to yt is the output why ht plus by. The output of each time step is computed from the hidden state, which contains summarized information of the sequence processed so far. When the hidden state accurately represents relevant past and present information, the output produced by the RNN becomes more meaningful and accurate. And here, if you are taking the example for this, the humanized example, suppose your teacher asks you questions in the class. Your teacher is asking the question in the class. Your answer depends on everything you have understood so far in the lessons. If your understanding is clear, your answer will be good. In the same way, the RNN gives its output based on how good its hidden state understanding is. Next, loss or error computation. Uh, Loss computation measures the difference between the predicted, this is the predicted output and the true output using the mathematical function LT is equal to YT minus YT gap the whole square. This value quantifies the accuracy of the prediction, where a larger loss indicates a larger prediction error and signals that need for stronger corrections during the learning. And the example for this case is after solving a mathematical problem, you compare your answer with the answer in the textbook. If your answer is very different, you know that you made a big mistake. If it is close, the mistake is small. Loss works exactly like this. It tells the RNN how wrong its answer is. Next, total loss over time. So in this case, the equation is given by L is equal to, that is in an RNN, errors can occur at multiple time steps and the total loss is calculated as the sum of losses across all these steps. And here the L is given by summation T is equal to 1 to TLT. The objective of RNN is to to minimize this total loss so that the model performs well consistently across the entire sequence. The example for this case is imagine a student takes daily quizzes for a whole week. Some days the score is low, some days it is high. To know how well the students performed overall, all quiz marks are added together. Similarly, an RNN adds error from all time steps to judge its total performance. Next one is the gradient definition. The gradient represents how much the total loss changes with respect to a particular weight. It indicates the sensitivity of the error to change in the weight and helps identify how responsible each weight is so for the prediction error. And here the equation is given by dou L by dou W. And if you are taking one real time example, if the student realizes that not revising formulas caused most mistakes in an exam, the student knows exactly what to improve. The gradient does the same thing. It tells the RNN which weights caused more mistakes and need more corrections. Next, BPDT, back propagation through time. In this case, it is given by dou L by dou W is equal to summation T is equal to 1 to T dou LT divided by dou W. In RNN, the same weights are used every time step, which means learning must consider entire sequence. During backpropagation through time, gradients from all time steps are accumulated to update these shared weights in a way that reflects the behavior of whole sequences. And if you take one best example for this case, a teacher checks a long answer paper where the same concept appears in many questions. Instead of correcting each question separately, the teacher gives one overall feedback for the concepts. BPTT works similarly. It combines learning from all time steps to update the same weights. Next, gradient flow through hidden state. So it is given by the formula dou L by dou HT is equal to dou LT dou HT plus dou L by HT plus 1 and into dou T plus 1 dou HT. Here, the gradient at a particular hidden state depends on not only on the error at the current time step, but also on error from future time step. This illustrates how gradients flow backward through time, allowing earlier hidden state to learn from later mistakes. The best example for this case is suppose a student misunderstands a basic concepts in the first chapter. This mistake caused problem in later chapter 2. When the student realizes that this at the end, they go back and fix the earlier misunderstanding. This is how gradient flow for backward through time. Next, weight update rule. It is given by this, everyone knows it of new weight is equal to old weight minus eta into dou L by dou W. Weight in RNN are updated in the direction that reduces the total loss, ensuring the improved predictions. The learning rate controls the size of each update, balancing stability and speed during training. And the example for this case is when a student notices poor marks. They don't suddenly study all night every day. What will do? Instead, They slowly change their study habits step by step. The learning rate the learning rate works like this. It controls how big each improvement step should be. Next, vanishing and exploiting gradient. This means the equation is given by multiplication of dou ht divided by dou ht minus 1. Due to repeated multiplications, this symbol represents this pi like symbol represents multiplication. Due to repeated multiplication of gradients across time steps, gradients may become very small or very large. And very small gradients, see here, very small gradients lead to vanishing gradients, making learning slow, while very large gradients cause exploiting gradients, leading to unstable training. So, the best example for this is imagine whispering a message through many students in a classroom. By the time it reaches the last student, the message may become too soft to to hear. The too soft means we are calling it as vanishing. If everyone shouts, it become noise and confusion, exploiting. This is exactly what happens to gradients in the deep learning networks. Coming into the summary, the forward pass computes hidden states and output for each time step. The loss function measures prediction error. Gradients are computed backward through the time step using BPTT, and weights are updated iteratively to minimize the total loss. So the example for this case is, generally speaking, learning in an RNN is like learning any subject. First you listen to lesson, then you attempt problem, check mistakes, understand where you went wrong, and slowly improve your performance over time. So, hope everyone understood about these concepts of the gradient in the or a need of gradient in RNN. The remaining things we'll discuss in the next class. Thank you.